So what I'm going to tell you about is charge and spectroscopy, but I'll start with a little bit of my personal evolution into this field, and then I'll continue with some of the things we're very excited about on infrared applications of those materials. I started with nonlinear spectroscopy. My first training was with Christos Philippe, and later on with Ron Shen at Berkeley, and we pioneered surface nonlinear spectroscopy with Jeff Hunt, who's now a fellow at Boeing Corporation. We did a lot of things that were very exciting. Then I came back to France, and I learned some electrochemistry from Tajuddin, who became an important administrator after that in the CNRS. And I did some of the first time-resolved experiment at surface, first with Yves Chabal, who was also a Bell Lab person. And then I did some other experiment. In my last year before coming to Chicago, I had 3 physical review letters, 2 of them as single author, and things never were that good after that. So I arrived at Chicago in 1991, and I was full of naivety and ambition, and I thought I'd do something interesting, finally. And I wanted to develop scanning tunneling microscopy to do single molecule vibrational spectroscopy. It sounded like a good idea. The STM was about 5, 6 years old. It seemed not so hard. I didn't know anything about STM, but you know, you've done good stuff. You think you can do more. So this was the plan, but it seemed hard, right? It seemed a little bit difficult. You had to learn STM, maybe cool it down. So I thought an easy step would be to do a nanocrystal STM spectroscopy. And so nanocrystals were pretty crappy things at the time. They were broad spectra. We didn't really know what was under those broad lines. Clearly very short lifetime transitions. But at least they were big, they were heavy, they wouldn't move too much, so it seemed that STM would be easy to do. But then also I still had to build the STM, so I thought at least the easiest part would be to do single nanocrystal spectroscopy using light, just light in, light out. Well, this was not very successful, all of this. Of course, single molecular vibrational spectroscopy with STM was done by Wilson Ho in 1997 in an absolutely beautiful experiment. Single nanocrystal STM spectroscopy was done by Oded Milot and using the nanocrystal by Yuri Banin, and that was a beautiful experiment, so that was gone. And so we were left with trying to do single molecule spectroscopy, and that was, we were basically following the work of Michel Aurit, which I think it's an incredible work that he did in 1990, and I think if there is a big prize in physical chemistry, he should be the one getting it. He really opened up the idea that you could look at one molecule by fluorescence microscopy in a very simple experiment. You just take an optical microscope, just shine light at it, use a filter, and see the molecule. In 1990, when I saw that paper, I thought this was an amazing paper. So it seemed really easy to do with a nanocrystal. They were big. They would fluoresce, so it should be very easy. So we started on that. 1983, I met Lou Bruce for the first time. He was giving a plenary talk at Chicago. And you know, he was already very famous. He was the plenary speaker. So at the end, I went to see him, and I introduced myself. I said I was interested in nanocrystal, and I wanted to do single nanocrystal microscopy. And I got kind of a cold shower there because he told me, why do you think it's interesting? So I didn't know what to do with that. I didn't know if he thought it was interesting and was just asking me to come up with some better ideas or whatever. But anyway, we still continued. And it turns out we were beat to it by Jean-Michel Girard, who did that for self-assembled epitaxial material. And about 3 months later, we reported our own single nanocrystal photoluminescence. Now, I thought we had an interesting approach to it because we're using 2-photon spectroscopy, and 2-photon was not done by anybody else. So this was the first 2-photon spectra of an individual quantum system, in a sense. And there was some easy aspect to it, that you just take an objective, take a fixed sample, have a dilute solution of dots, and it's automatically confocal. So we didn't have to do any fancy piezo adjustments or mechanical adjustments of the focal position. We would always find a dot within about a micron cube in the sample. So it sounded really nice. And the other thing that I wanted to do with it was photoluminescence excitation spectroscopy just across the exciton line. And in principle, because it's 2-photon, you don't see the laser light, you only see the fluorescence. So you can go right do high-resolution spectroscopy right around the fluorescence line. Well, it turns out it was not that easy. First, we had to learn how to make nanoparticles, and we had to get this two-photon experiment going. It turns out that we estimated the two-photon cross-sections. They were very large. That was not going to be a problem. But we had to get a picosecond laser. But anyway, Sean Blanton was my first student, and he did that work, and we got this work done. Well, the paper was rejected by Science, but Lou Bruce was very kind. He was editor of Chemical Physics Letter, and so we sent him a letter saying, Lou, would you mind looking at this paper and tell us if it's okay? So it got published in Chemical Physics Letters. But anyway, still, we lost, because a year later, or a little bit more than a year later, 2 years later, Munji Bawendi and Lou Bruce joined forces to do this beautiful work on single nanocrystal at low temperature using one-photon spectroscopy, which turns out to be so much easier. And Lou Bruce and Munji and Nirmal saw this amazing blinking that we couldn't resolve because, although we saw fluctuations, our acquisition time was about 30 seconds just to get enough photons. We continued this work for a little bit more. In fact, this paper was rejected by PRL, so it took about 8 months to get it published. So we lost again on this time scale. But again, our data were not as good. Two-photon spectroscopy of single particle was just not as nice as one photon. So that was a lost race. We still learned some things. We did two-photon spectroscopy. We had some very nice two-photon excitation spectra of particles. This was using the recently published work of Munji Bawendi, Chris Murray, and David Norris. Chris Murray was very kind. He let us have his thesis so that we could just have all the details about the synthesis of their new material. So that was ATP, as I like that. This was a comparison of the one-photon spectra and the two-photon spectra. So you see they're very different. But the peak kind of fall in the same place, even though they have very different amplitude. That's not that surprising based on the selection rule. What was interesting to us was that the near edge or the band edge features were very similar. So it didn't seem that there was a strong selection rule between an S-like transition or a P-like transition. And also you can see here the two-photon spectra has really no scattering line, which was our initial motivation to do two-photon single particle spectroscopy. Still an experiment that needs to be done. The spectra were calculated or simulated using the theory developed by Sasha Efros, which was first reported applied to cat selenide in that JOSA paper that he mentioned with Christos and Alexei. And then we also used the paper that was just being published by David Norris on their beautiful matching of the one-photon spectra with the theory. And this is our attempt to do the matching with the two-photon spectra. So the lack of a clear selection rule led us to some other direction. We thought maybe there's a dipole moment in that structure. And so we looked for the dipole moment. That was one of Sean Blanton's success to be able to measure a permanent dipole moment in those small particles of cat selenide. And initially we thought it's simple, it's just a vert-size structure, so it is polar, it has to have a dipole moment. Later on, Moonsub Shim made the same measurement on other particle, and we found that the dipole moment was always there as long as you look at an insulating particle. And that made us first time aware of the idea that charges are going to be decorating a surface of an insulator, and as a result, there will always be some effect of charges or dipoles. So this was the lost race. The one race, as Sasha very kindly reminded you, was the core shell. So as Lou Bruce said, and then later Munji in his presentation, they did try to make nice, bright cat selenide zinc sulfide quantum dots, and they did not succeed. And there was another work, of course, that was mentioned by Eichmüller and Horst Weller on this very nice system here. That system didn't really take off. It's a very nice system, but it didn't really take off. So Peggy Hines here was an organometallic, trained as an organometallic chemist, and she joined my group. Initially, she was working on some frequency generation and surfaces and all those nonlinear optical coefficients and Fresnel factors. That was not her stuff. And then at one point, she saw Sean Blanton and I struggle with, we didn't have a glove box. We had a plastic glove bag, and we were doing dimethyl cadmium distillation in it. So she saw us struggling with this, and she said, I think I can help. And so she started working on the cat selenide nanoparticle. I think she interacted with Chris Murray at that point. And And we thought, we need to have them bright because we want to do single particle spectroscopy. So can you make them brighter, Peggy? And she worked, and I said, well, why don't you try putting a zinc sulfide shell on it? And she said, okay. And she figured out how to do it on her own. She took diethyl zinc and made it. And one day, one night, I don't know what time of the day it was, probably at night, she is the one who saw the very green, room light fluorescent of those particles. And so it's her credit. So, but we didn't have a TM, we didn't have XPS, we didn't have XRD. So she went everywhere around Illinois to do this. She went to Urbana-Champaign, she went to UIC, she went to Argonne National Lab and characterized his sample, and there they were. They were what we call core shell. We sent the paper to JPC. The referee not rejected it outright, but said, it's not really a great paper, and you shouldn't call it core shell, you should call it zinc sulfide capped. So that it is, zinc sulfide capped. So that was a very nice work, of course, of Peggy. And she went on to do some other nice things, of course. And that work was followed up by the group of Munji. I met Munji in 1995 at the ACS meeting. That was the first time. We had a very nice lunch along the Chicago River. It was really a great pleasure to meet him because, of course, he had done that beautiful work with Chris and David on the ATP-BTP boundary. And he told me point blank that they had worked on the wrong system because they had focused on cat selenide, zinc selenide, based on their previous experience that cat selenide zinc sulfide was not working. And so when he went back to MIT, what I heard many years later, mostly from Hedi Matusi, was that he basically told his group, get working on cat selenide zinc sulfide. So about a year and a half, he had some very nice work, of course, in that topic. Our dots were pretty good. And Shuming Ni came by the lab in 1997 and wanted some of those dots. They were not available commercially. And he wanted to do some Raman spectroscopy on it. And so he did that. And then about a year later, I get an email from him, or a mail, I think, and I see a paper that's, he said, is about to be submitted into Science. And I read the paper, and I thought, well, that's not really nice. That's not really very, no physical chemistry, no new concepts of physical chemistry, not very interesting paper, obviously. And it was published in Science, and the rest is history. Obviously, I wish I was a co-author of that paper, but I didn't think it was worth myself. So anyway, they did use our dots, and they wrote it this way, developed by Heinz and Guyot-Sionnest, but in fact, they used the dots that Peggy had given them then. So this was an exciting moment, of course. This is the picture of quantum dots that was taken in Chicago. I was very pleased that Munji used that picture as the introduction to his talk. It's just a solution of colloidal dots in pipettes. It's sitting in front of my office. It was taken by Jason Smith. In case you'd like to use it, please feel free. So we worked on the core shell for a little bit longer. We worked on two-photon spectroscopy, but it was clear that we needed to do something else. So I was very interested in the broad spectroscopic features of those particles, and I was wondering whether the prediction of those higher excited states was real, what was under those broad bands. And at least one prediction of those electronic structure by Sasha was that there should be a series of nicely high-lying states, especially in the conduction band, that should be well isolated from each other. And they would be perfectly tunable in the infrared, and my background was infrared spectroscopy. So it seemed very natural to try to detect those transitions, and they are called intraband transition. And it worked beautifully, so we had samples here of the cat selenide, and when we do a pump probe spectroscopy, we saw those very intense infrared transient absorption, which tuned with size, had about the right cross sections, and had the right tuning. And I got very excited by this. And so I thought, it's very simple. Now all we need to do is to find a way to put electrons in here, and then we will have a system that's infrared active. We can make detectors. Intraband detectors were very popular at the time. The work of Capasso on engineering quantum well system was very interesting. So I thought this would be a very nice, simple way of making this complicated structure. And so there are some challenges. They were very broad line widths, so was that homogeneous or inhomogeneous? So we ended up solving that question. It's inhomogeneous. Can we dope it? And so that's still a question. Can those things conduct? Can one make a photodetector out of that? And what about the relaxation? I mean, suppose you do put the electron here, how fast does it come down? So there are a lot of questions. The charge doping was a question, and so we were interested for this reason, but over the years there have been, of course, a lot of other points where it became important. And so the question is, can we put a carrier? Can we make a negative quantum dot? Can we make an ionized quantum dot? And in the 80s, this was a common thought in the sense that quantum dots were motivated by photochemistry and solar energy conversion. So one wanted to photoexcite the system, separate the carriers. Most of the time, there would be a charged carrier left. This work was carried out already by Henglein, Kamat, Nozick, Weller, all of these very famous people from the early days. And Lou Bruce had this very nice paper where he specifically discussed how the energy of a charged dot would vary with size. Unfortunately, all the experiments on reduced or oxidized quantum dots didn't work in the sense that they were not stable. So you'd oxidize or reduce the dot, and some chemistry would go on, and the dots would degrade. So it was not obvious that it would work. In particular, it was not clear that there would not be many states that you'd have to charge before you could charge the quantum dot states. The surface is obviously a messy proposition in quantum dots. This was kind of a lucky thing. Of course, nature decides what we can see and can't see. And this was done by Moonsub Shim. So we were looking for ways to inject charges in quantum dots. And I told him, well, just take a chunk of sodium, put it into your test tube, and look for the spectrum. And he tried that, and it didn't work. But he's very smart. And one morning, I come back and say, you know, I saw something interesting. I used sodium biphenyl and put it into the test tube, and I saw this beautiful infrared absorption. And he discovered the way of doping, charge transfer doping a nanocrystal. And it was very nice because this exciton peak disappeared in the presence of the biphenyl. This infrared absorption appeared, and we knew what that meant. That meant that the electrons were in this state, and we could see this infrared transition. And also, this exciton peak disappeared here because of the occupation of the state. So it all worked. It turns out a couple weeks later, he did check the sample that had sodium in the test tube in the glove box, and it was the same spectrum as this. So it did work eventually. Electron did get transferred from the sodium chunk to the quantum dot solutions over time. We continued a lot to work on this charge transfer doping. We tried to use electrochemistry. This was started by Songjun Wang. One thing that we were very excited about was the possibility of changing things like the stimulated emission, first reported by Viktor Klimov, but changing it by adding carriers in it. And yes, the fluorescence decreased when we made negative quantum dots, but what we found was what we expected, which is that because the system becomes transparent at the lasing wavelength, the gain is in fact higher. And so what we found, Songjun Wang, and that was, I was not there when he found that, it was in the middle of the night, and he found that the quantum dot had this threshold, and just by switching the potential a little bit, just to make the dot transparent at the emission wavelength, he found that the threshold was reduced by a significant amount. He was very happy when he saw that, because I told him, this is great, you're going to get that published into Science, it's going to be very exciting. And so he went dancing in the street in the middle of Hyde Park, and when I saw him in the morning, he had a crooked smile, because something happened to him. He just fell from the sidewalk and broke a tooth. So the paper was not published in Science, it was rejected. It was eventually published in Journal of Physical Chemistry, and that's all right. So, but that was exciting, and I think it's going to be something for the future, of course, to charge the dots and try to make them laze better. So there was a mystery, blinking, which was intimately connected with the charge, and that was because of Sasha. So Sasha proposed that a dot once in a while gets ionized, and if it's ionized, then there would be an Auger process, like if you create an exciton, there would be a very fast non-radiative process where the electron recombines with the hole, kicking the other electrons far out, and then that electron would just recombine non-radiatively to the bottom of the band. And so basically, the electron catalyzed non-radiative recombination. And so that was Sasha's and Efros and Rosen mechanism. And we were charging the dots, so it seemed like an obvious thing. But we had made the dot laze when they were charged, so clearly they were not that dark. And so Efros and Guyot-Sionnest had a fight. And there we go. And it's a fight where we speaks Russian, I speak French, we don't understand each other. This is what Chassaud was saying, charged dots are dark, and I was saying charged dots are not dark. And we kept on going like this for years. Eventually, I think we at least could show that negative charged dots are not dark because we could measure their PL. We could see that, for example, a negative charged dot has brighter PL at early times, even though on the integrated PL it's weaker. And so we were able to finally, we certainly were convinced already, but we were able to convince others that the negative trion is not dark enough to be the dark state in blinking. So then we started looking for a bright negative trion. And we were not the only one. There was some work in the literature that started to show that negative trions were also bright. There was this work by the people down under in Australia. They found that they could look at a single dot at cryogenic temperature and see lines that were associated with charged dots. And there was the work by Lunis, which also show charged dot. And of course, there was the work by Benoît Dubertré and Jean-Pierre Amier, where they saw this amazing thing that a charged dot could have 100% quantum yield. All of those were low temperature. And so it was, I think it is an interesting question whether one can get a bright charged dot at room temperature. And so we searched for that. We developed this technique, which is to do electrochemistry on a single dot and to try to see the dot and with a charge on it. This was the first time we went back to single dot spectroscopy after the traumatic experience of the 1990s. And what we saw was that the dot could very well be charged and turned off on a regular basis like this. But the charged dot in this case with zinc sulfide cap was just plain too dim to see. And so this is the spectra of the dots uncharged, and when it's charged, it's just matching the background level. This is the dot blinking as the potential is stepped down to the reducing potential, and at some point it just stops blinking, stops emitting altogether, and then it comes back. So then we tried other kinds of dot. This was a cat selenide sulfide alloy dot, very broad, single dot, neutral emission. Not so clear why it is so broad. But clearly what was nice was that when it was charged, then it was no longer blinking and it was observable. So charged dots do not blink. And I think the reason is that the blinking is suppressed by the electron, which scavenged the highly oxidizing hole. But still the challenge was to bring this up. And what we're looking for was a bright charge small dots at room temperature. So we started looking into the type 2 core shell structures where in principle the electron and the hole are separated so that the Auger process in this simple interpretation would be reduced or eliminated. And so we looked at this cat telluride, cat selenide, did the synthesis, see the huge Stokes shift. This was not new. Saw the lengthening of the radiative lifetime. Everything matched. And then we looked for the trion of those. And what we found, and that was very surprising, was that, and that's fairly recent work, that's just last year, what we found was that the trion lifetime or the charged dot lifetime gets faster, of course, than the neutral dot, but it's non-monotonous. It's not simply extending the range between the electron and the hole does not monotonously increase the trion lifetime. There seems to be a peak. So the trion lifetime starts short, gets longest at some intermediate shell thickness, and gets short again. So it's very strange. So the first time Wei Qin saw this result, I told him, well, maybe it's a problem of growth, and you get some defects after some thickness of shell, and things are going wrong. So he tried a different synthetic approach for the shell, did, of course, his TEM work, and then tried a different core to see if this would happen differently, and he found more or less the same thing with a different core. So that was fine, and then we said, well, we better check the biexciton lifetime. It should show the same effects, this kind of non-monotonous behavior. Biexciton lifetime shows this simple monotonous behavior, matching more or less the observations by many previous experiments, in particular the work of Viktor Klimov on the scaling with size. So there was this kind of bizarre things where the negative trion lifetime is non-monotonous, but the biexciton lifetime is. And I think it's still a topic of discussion. The paper was rejected initially by ACS Nano. Eventually, I pleaded with Andrei Rogash, so it's nice to know people in the field, and he managed to publish it. This is verification of the beneficial effect of that intermediate shell thickness on the single dot level. So this was the blinking of a single dot, and then we stepwise make the potential reducing, and we find that it stops blinking. And it's more or less as bright as when it was in the neutral state, and then it comes back. Now, this is Wei Chin who did this work, a very brilliant young scientist. And so what we found was that it seemed as if this optimum in the trion lifetime was obtained when the shell is just big enough that the electron state is skimming the bottom of the conduction band of the core, which is where the electron has exactly zero kinetic energy in the core. And so intuitively, it seemed as if the electron has zero kinetic energy, then maybe that's why the electron-electron collision doesn't really happen with a hole. And certainly in the bulk, if the electron has zero kinetic energy, there's no Auger process. So it kind of makes sense, but it was very hand-waving. So we looked for a slightly less. This is just the variation from dot to dot. This is the champion dot. We looked for a slightly less qualitative explanation, and then we ended up looking into this matrix element that Sasha has told us to look at, which is the Auger relaxation process, where we've got this Coulomb interaction between the electron states, the two electrons, and then the hole that. And what you find is that it's really the overlap of the whole wave function and the electron wave function that matters. The electron, the particle has to be at the same position in this wave, in this matrix element. And before that, in the same way as Victor before, we always thought of those as being the envelope function. So clearly, as you build the core shell, the envelope function go further apart, so that would be fine. But the fact is it's not the envelope function, it's the envelope function and the block function. And so it's very important to also consider the block function. And what we realized was that if we have zero kinetic energy, then we have a pure S-like block function of the electron and a pure P-like block function of the holes. There's actually zero spatial overlap. They are on separate spatial position. So that should be identically zero. But as you move away in the conduction band, as you pick up kinetic energy, either with the real wave vector or the imaginary wave vector, you start mixing in the P atomic orbital or block function with the S one. And so now you can imagine that you're going to get some spatial overlap. And so the idea was that as the spatial overlap is big, then the coupling becomes stronger and the trion lifetime becomes shorter. And so really there's this optimum point here where the trion lifetime should be the shortest. So that's a proposition. I haven't heard yet from theorists published, of course. I haven't heard yet from theorists whether it's crazy or not. But that's where we are in our search for understanding further the Auger and making bright dots. So I'd just like to mention some of the Auger facts and mystery. It was very nice to see Sasha mention this early work from the Palaiseau group. And then I'd like just to say that there are many things that are not clear in Auger, at least to me. There are many orders of magnitude discrepancy in the bulk theory and experiment calculation of Auger rate. There's, of course, the beautiful results of Viktor Klimov, the R-cube dependence and the universal biexciton lifetime, which makes absolutely no sense to me, but it seems to be a fact. We looked into this, and we tried to tweak the whole wave function and to see if that had an effect on the Auger. It should have, according to this matrix element, but it doesn't. That's in JPC 2007. We tried very hard to tweak that Auger biexciton lifetime, moving the whole wave function. It doesn't work. And then we have this now results from many groups of very long-lived, high quantum yield trions, negative trions. And then we have this prediction in the single electron picture that there should be an additivity between the X minus, X plus rates for the biexciton. I think it still remains to be proven because the X plus is very hard to measure. So I think it's still a very interesting problem to investigate. There are some funny facts and some interesting mysteries with Auger. So in summary of this part, charged dots are not dark. Charged dots do not blink. We propose a new idea for how we can tune the Auger relaxation of the negative dots. And Auger is very unclear to me. I think there may be some, there was a question earlier about correlation. I mean, I think whole transitions, energies, whole energy states are very close by. It's very congested. They typically are separated by 10 millielectron volt. Coulomb interaction is 50 millielectron volt. So it wouldn't be surprising to me that there is some correlation coming up at the level of the holes, at least in the 2.6. So this is something that I thought was funny, but maybe it's not funny at all. This is about photovoltaic quantum dot community. This was after Victor showed the 700% carrier multiplication efficiency. Everybody rushed to try to make photovoltaics. Munji said, hold on, it's not that efficient. So everybody kind of took a slightly more conservative course. So this is Victor, this is Art Nozick. Actually, now Munji is here. They just published something in Nature, but all those guys can swim, so I'm not worried for them. We tried something different. So we tried to work on infrared. I'm just as silly. I think I can fly. And I think that quantum dots may have a role for infrared, but so far I'm kind of alone in this topic, so it's really silly, I guess. So we want to work on infrared quantum dots. This is not a real picture, of course. So this is the infrared that I'm interested in, at least. There is the mid-wave infrared, where the atmosphere is transparent all the way to space, 3 to 5 microns, looks at hot objects around 600 to 1,000 Kelvin. And there is the long-wave infrared, which looks at warm body objects, our cells, 8 to 12 micron, also transparent all the way through to the atmosphere. And this is me in a garbage bag, maybe my natural state. But if you look in infrared, you can see how many fingers I'm holding. Through the bag, I have 5 fingers that I'm showing here. And so the infrared allows you to see things that are different. And of course, there's no backlight here. This is just the thermal emission through the polyethylene going through. So infrared is interesting because, to me, it's a very expensive technology. It takes about $100,000 if you want to buy a nice infrared camera that works in the long wave. There is slightly cheaper technology, which is very nice bolometers, but they're slow. And so they wouldn't be able to do a video recording of, for example, a hench moving like this would be just a blur. And so quantum dots may have some role to play in this because they're always cheap, right? They have easy to put onto a surface, easy to process. Now, there is something special about quantum dots, which is that there is no organic competition with the infrared. You know, we always say we make this nice core shell dot, they fluoresce, but organic dyes fluoresce beautifully. Organic LEDs work beautifully. So quantum dots have to work hard to make it competitive. But in the infrared, at least there's no dyes, so that's good. So that's why I chose to work in this area, and also, I guess, because of my background in infrared spectroscopy. So one approach is to use interband dots, so trying to make take smaller and smaller gap bulk materials and just make quantum dot out of it. So the ternary materials are very promising, but you need to be a good chemist to control the composition accurately. So we look for simplifying. Semi-metals is the other option, things with a zero gap. So for example, bismuth, antimony, graphene, very exciting at the moment. And of course, the mercury chalcogenide. And so mercury chalcogenide have been explored before by the Vela group. So Rogash, Eichmüller, that I didn't mention on the slide, sorry, Alex. Maxim Kovalenko and Wolfgang Heiss did some really nice work. Ken Kuno did some nice work, and Mark Green in England. So this materials has been explored, and it seemed like a nice thing to start. And of course, my colleague, Dimitri Talapin, changed or made it a lot more attractive because he discovered those inorganic ligands that may not have any vibrational absorption in the mid-infrared range. So looking at mercury telluride, it's a zero band gap. It has a simple band structure. The electron has this nice dispersion. Seemed really ideal, but you never know when you make a quantum dot if the surface is going to screw up things. So I had one brave student, Sean Killian, who decided to work on the mercury compound. And he developed a synthesis that was better than before, which allowed him to get this wide range of tuning in the mid-infrared from covering fully the 3 to 5 micron range with fluorescence as well. So that was nice. And then soon after he did this and got the first evidence of photoconductivity, we were joined by Emmanuel Huillier, who had an expertise in infrared detectors, and he really pushed us forward in this direction for his hard work, creativity, and great ideas. And so these are his data on the photoconductivity of mercury telluride quantum dots, simple films drop cast onto interdigitated electrode and stuck in front of a standard commercial Fourier transform infrared spectrometer scanning quite fast. So the white line of the interferometer line goes through in about 100 microseconds. So they're a very good detector. He characterized, of course, the response speed. You can find that information in his paper there. So that worked pretty well. This is just on the edge of the mid-infrared. This is smack into the mid-infrared. This is extended a little bit further down to 7 micron at low temperature. We extended this a little bit further since he left. Now we can go further into the long wave IR. So this is a dot that responds pretty nicely. At low temperature, we're just entering the long wave IR. If we try to go further, it gets hard, and the signal drops dramatically, but it looks like there's no intrinsic limitation to go there, but of course, it's a signal-to-noise issue eventually. So this is the current performance that achieved so far. This was done by Emmanuel Villiers. So this was the first dots compared to the existing single crystal or epitaxial technology, so a couple of orders of magnitude to gain. This was his latest results with the arsenic sulfide. As he jokes, if he works with mercury, he just makes it more fun by adding arsenic. So then that's pretty good. And so, of course, we need to do the same thing for the long wave IR to characterize their responsivity and detectivity. So I think this is a promising direction. Mercury telluride quantum dots is just another kind of quantum dots. I think they may become competitive in the infrared. Certainly worth investigating further. They may allow higher temperature. And this certainly should have a cost processing advantage. And they may be coupled with plasmonic enhancement because they don't need to be epitaxially grown. They can just be drop cast or spin coated and so on and so forth. So these are the heroes of this work. And of course, we were lucky to get some funding. So now I'd like to go back to a topic that has been of long time interest for me, which is, can we make some infrared photophysics with the intraband transition? And that's hard because what we want to do really is to take a quantum dot, imagine zinc oxide, transparent, but it has those nice intraband transition. Well, we can charge zinc oxide by UV light, but let's put 2 electrons in it. And could we make, for example, an infrared photodetector out of zinc oxide? The dots are not the same size. It's highly disordered. We need to have exactly 2 electrons per dot, so we have a nice conductivity minimum. We need to have the electrons easily go from dot to dot, so there was a lot of things to solve. One thing that was promising was back in Science 2003, we showed that the mobility of the electrons in the p state was about 10 times larger than the mobility of electron in the s state. So there is some hope. It's time now? Almost. Okay, good. So we got a break. The question was how to put 2 electrons in a dot. And we were lucky. We explored the other mercury chalcogenide. Mercury sulfide seems to do that by itself. You take mercury sulfide and you find this intraband absorption, and it's very sensitive to surface. So you can just dope it and undope it by putting mercury-rich or sulfur-rich on the surface, and we attribute that to a surface dipole effect. So there is a system that is naturally doped, and if you control the doping, you get just 2 electrons in that lowest quantum state. It fluoresces. The intraband absorption leads to fluorescence, and it's just about the same quantum efficiency as mercury telluride interband emission. So that's the first case of intraband PL. It's very promising, of course. It tells us that the system is well behaved, that there's no states between the 1p and the 1s transition that would quench the luminescence more than it should. And so this is our first intraband photoconductor. So we take those kinds of materials and we can measure, in good cases, we can measure room temperature photoconductance. And now you see it's just a peak. It's not a broad absorption with an edge. It's just a single peak where the intraband transition is. And at low temperature, we get a very decent signal to noise. So I'd just like to summarize. Colloidal quantum dots, as we all know, are little beacons of light, and they can go from the visible to the infrared. I tried to emphasize that charge played an important role in the photophysics. And I'm, of course, very happy that just this time to be with all of you and to also share some of the excitement we feel after 15 years of research on intraband transitions. And most of all, I need to thank all the people who worked in my group. These are all my past PhD students. Some of them you know. I mentioned those that are highlighted in black and underlined. And these are all my past postdocs. And this is the current group. And thank you so much for your attention.